Good morning, children. So, today I am discussing the last topic of the electromagnetism chapter, that is electromagnetic induction. So, what is electromagnetic induction? That you will learn by performing one experiment as we did for the other topics. Okay. So, you see here the fantastic experiment how to perform. You have taken a coil. There are several number of turns, and at the two ends of the coil you see one galvanometer is connected. No other source of electric current is there in this one. That is the most interesting thing, and you have to observe that. Now, you have taken one pole of a magnet. Here I have written North Pole, but that is not mandatory. You may take any pole. Alright. Now what is done? This north pole is brought near the coil. That's why you see I have given the arrow. So arrow indicates the north pole is moving towards the coil. Alright. So when the north pole will move towards the coil, then you will see as long as the north pole is moving towards the coil, galvanometer will deflect. Alright, and if the north pole moves towards the coil, then you will observe that current will flow in this direction. Alright, and the galvanometer, it will deflect in this direction. Alright, so you see here, there is no source of current, but still the galvanometer is deflecting. What does it indicate? That an EMF is induced in the coil. Alright, question will arise when the EMF will be induced, as long as there is a relative motion between the coil and the north pole. Alright, between the coil and the north pole. Alright, you will observe that galvanometer will deflect. The moment you will stop the north pole, then what will happen? No deflection in the galvanometer. Alright, then third observation. Instead of taking the north pole towards the coil, if you take the north pole away from the coil, then you will observe again, as long as the north pole is moving, galvanometer will deflect, but now it will deflect opposite to the previous one. Alright, so why it is happening? Why it is happening? Because magnetic flux, when there is a relative motion between the north pole and the coil, then magnetic flux linked with the coil changes. As a result, an EMF is induced in the coil, alright, and as the circuit is closed, a current passes through the coil. So this phenomena is known as electromagnetic induction. Now, if you want to know about electromagnetic induction, first of all, you have to know what is magnetic flux. So, you see, what is magnetic flux? Magnetic flux is number of magnetic lines of force crossing any area perpendicularly is known as magnetic flux. Alright. So, just try to understand it. Here I am drawing the diagram. When the coil is like this and the north pole was here, then you see, all of you know that from the north pole, the lines of force, they are coming out like this. Yes or not? The arrows are away from the north pole. These are the lines of force coming out. Now you see, when the north pole is far away from the coil, then you see few number of lines of force only crossing the coil. Just you consider this example. If I extend it, then only these two lines of forces are crossing the coil. Alright. So, magnetic flux linked with the coil is how much here? These two lines of forces crossing. So, it will be 2. They are crossing perpendicularly, if I assume. Okay, here this point is very important. The lines should cross the area perpendicularly. Alright. Now you see what is happening. When the north pole is moving towards the coil or moving away from the coil, then what is happening? then what is happening? Magnetic flux linked with the coil changing. Yes or not? Just you see, when the North Pole is moving towards the coil, then what is happening? Number of lines of force, more number of lines of force, as the North Pole will come towards the coil, more number of lines of force will cross the coil. It means what? Magnetic flux increasing. Magnetic flux linked with the coil increasing. But if you take the North Pole away from it, then what is happening? Magnetic flux linked with the coil decreasing. But in both the cases, what is happening? Magnetic flux linked with the coil changing. That is the most important point. Okay? And what is electromagnetic induction? Electromagnetic induction is the phenomena in which EMF is induced in the coil. When EMF will be induced? When there is a change in magnetic flux linked with the coil. Alright. So, what you have to learn? You have to learn first the definition of the magnetic flux. What is magnetic flux? Already I mentioned. Number of magnetic lines of forces crossing any area perpendicularly is known as magnetic flux. And what is electromagnetic induction? It is the phenomena in which an EMF is induced. An EMF is induced when there is a change in magnetic flux linked with the coil. Alright, there is a change in magnetic flux linked with the coil, then that phenomena is known as electromagnetic induction. Alright, so this electromagnetic definition of electromagnetic induction and magnetic flux you must learn. So here just one point you must remember, that when EMF will be induced, when there is a change, this term is very important, change. There should be a change in the magnetic flux linked with the coil. Alright, and when the magnetic flux will change? When there is a relative motion between the North Pole and the coil. Here you see, when we have performed the experiment, I said that coil I have kept fixed and North Pole is taking towards the. Now you can do this, you keep the North Pole fixed and you can take the coil towards the North Pole, then also the same thing will happen. Alright, means electromagnetic induction will take place and EMF will be induced. Now here, one point, another point I prefer to mention. Here I have taken a coil which is closed by a galvanometer. Alright, but if you do not take a coil which is not closed, then what will happen? EMF will be induced, but as the coil is not closed, current will not flow. But when the coil is closed, then what will happen? EMF will be induced as well as an electric current will pass through the coil. Okay, so you must learn what is magnetic flux and what is electromagnetic induction. Now next is, whenever electromagnetic induction takes place, it obeys three laws. Okay, the first two laws given by Faraday. So after his name, it is known as Faraday's laws of electromagnetic induction. Faraday's laws of electromagnetic induction, and Faraday gave these two laws just performing that experiment already I described. Okay. Now, what is the first law? First law, what is the observation? That is only in the statement if you write, it will be the first law. What was the observation? That whenever the magnetic flux linked with the coil changes, an EMF is induced in the coil, and the EMF persists in the coil as long as there is a change in magnetic flux. Okay, means there is a relative motion between the coil and the magnet. Okay, it may not be magnet, it may be a current carrying conductor also, because you know current carrying circular loop, it also behaves like a pole. Alright, so you see what is the statement for the first law. As you know, that statement of a law you cannot change by your own. You have to follow whatever exactly given. That's why the first law statement everybody should note down and learn and remember. That whenever there is a change in magnetic flux linked with the coil and EMF is induced. And the EMF induced lasts how long? So long the magnetic flux linked with the coil changes. Alright. Now, second law gives you the idea about what will be the magnitude of the induced EMF. And according to Faraday's second law, that magnitude of the induced EMF, it is directly proportional to the rate of change in magnetic flux linked with the coil. And you know, rate of change means divided by time taken. So you see, you can write that what is the second law? The magnitude of EMF induced is directly proportional to the rate of change of magnetic flux linked with the coil. So you see, you can write induced EMF, it will be equal to number of turns of the coil into change in magnetic flux of each turn. So you see, if delta phi, this is phi, and delta always represent what? It is not samosa, it is delta. Another point you must remember that it is not delta into phi. We write it together. And already several times I explained this one, that whenever we use this symbol delta in physics, before any quantity, it represents the change in that quantity. Just like if I write delta V, what does it mean? Change in speed. Okay, so delta phi is used to represent the magnetic flux. Okay, so here you see delta phi represent the change in magnetic flux, but be careful, this is the change in magnetic flux associated with one turn. And if there are n number of turns, so what is the total magnetic flux change? It will be n into delta phi divided by time in which flux changes, and that is denoted by delta t. As I already mentioned, delta represents the change in the quantity. So this is the formula we are getting from Faraday's two laws. Alright, here you see one more thing. I said it is directly proportional, but in the formula equal sign is given. So it is understood constant of proportionality is 1. Another point I have given here, negative sign. Alright, this negative sign indicates you the direction of the induced EMF. This negative sign has no role for the magnitude. Okay, so be careful. This negative sign is associated with the direction of the induced EMF. And what will be the direction of the induced EMF? That is given by Lenge's law. Now, what is Lenge's law? Lenge's law is, as I said, it gives us idea about the direction of the induced EMF. What Lenge's law states? It states that direction of induced EMF should be such that it opposes the cause which produces it. Alright, so let us understand it from the experiment we have done first. Alright, we have taken a coil whose two ends were connected with a galvanometer, and what we were doing, we were bringing a north pole towards it. Okay, then I hope you can remember, I drawn in the diagram that current will be in this direction. Alright, now how I said to you that current will be in this direction? Alright, that you have to understand it. So, let us find out. Here you see, Lenge's law said what? It opposes the cause which produces it. So, this part is most important. First of all, you have to understand, you have to decide what is the cause of the EMF produced. So, let us find out here. What is the cause? North pole approaching. That is the cause. Clear? Now, what you have to do? Direction of EMF should be such that it should oppose the cause. Means what? EMF should be such that this will not allow North Pole to come towards it. I repeat, what is the cause? North Pole coming towards the coil. What the EMF will try to do? It will not allow North Pole to come towards it. How it can do? by creating a north pole here. Isn't it? So you see here, when a north pole will be created, then this north pole will repel this north pole, means it will oppose the cause. The cause is north pole approaching towards the coil. Here if one north pole is developed, then it will oppose the cause. So you see, I kept that point in my mind and I have drawn the diagram. So here one north pole means current will move in the anti-clockwise direction. So when the current is moving in the anti-clockwise direction, then you see the direction of the current will be this direction. So it means the current is coming like this. So through the galvanometer, current will enter and then it will move in this direction. So in which direction galvanometer will deflect? In this direction. Is that clear? So you see, Lenz's law helps us to decide what will be the direction of the induced EMF, direction of the induced current produced in the coil. And this application of the law is most important. And in the sample test paper, whatever we have got from the board, that the sample test paper is there. After finishing the theory part, I will try to discuss it. Okay. But this is the way the Lenz's law is applied. Just I am giving you one more example. Suppose here, instead of bringing a north pole, you are bringing one south pole. Then what will happen? And south pole you are bringing towards it. Then what will happen? Which pole should be created here? Here one south pole should be created. Because you see, then only it will repel and it will oppose the cause. What is the cause? South pole approaching. Alright. So how to oppose? One south pole should be there so that it gets repelled. Then south pole means what? In which direction current will flow? Current should flow in the clockwise direction. So clockwise direction means through the galvanometer, current will move towards the left. So in which direction galvanometer will deflect? Galvanometer will deflect towards the left. Is that clear? Now suppose you want to take the south pole away from it. So south pole away from it. Then what will happen? What is the cause? South pole is moving away. That is the cause. So current should not allow the south pole to move away. So which pole should be created here? North pole. Because if north pole is created, then north and south will attract each other. So it will not allow the south pole to move away. It will oppose the cause. So if north pole is created, current will move in the anti-clockwise direction. So when the current will move in the anti-clockwise direction, then you see galvanometer will deflect in the opposite direction. Alright. So that's why you see, if anybody want to mug up this situation, then definitely will fail in exam. Okay, fail to perform to write the correct answer. So you have to understand it, how to apply the concept of Lenz's law in determining the direction of the induced EMF or the direction of the induced current. Now, there is another rule by which one can find out what is the direction of the induced current. Okay, that is given by Fleming's right hand rule. I hope you can remember that when a current carrying conductor is placed in a magnetic field, then the conductor experiences a force, and the direction of the force experienced by the conductor in which the conductor moves, that we can find out by Fleming's, this is my left hand, Fleming's left hand rule. Alright, so in the Fleming's left hand rule, what we did, the first three fingers, the thumb, index finger, the middle finger, you set it perpendicular to each other. Then I hope you can remember, I said father, mother, child. Father means the direction of the force in which the conductor will move. Mother, M is the magnetic field. Then current, C, child. So C is the direction of the current. Alright, exactly in the same manner, the Fleming's right hand rule is, this is my right hand. You set your three fingers of your right hand. Three fingers of your right hand perpendicular to each other. Alright, then you see, here also you can apply the same thing. That is, F is the force, then M Again, that father, mother, child, as I said, F stands for first, thumb stands for first, then the index finger, M, mother, and the middle finger, C, child. Alright, but here what is the meaning? Little bit change is there. Here, F, force, means in which direction the conductor is moving. Then this is the magnetic field, and then this one is the direction of the induced current. Alright, middle finger is the direction of the induced current. Alright, so here one point you have to understand, when to apply Fleming's left hand rule and when to apply Fleming's right hand rule. In Fleming's left hand rule, you see there that there is a current carrying conductor. Okay, current is moving in this direction. You have placed in a magnetic field. That's why the conductor is moving in this direction. Alright, but in this case what is happening? Conductor is moving in the magnetic field. Okay, so conductor is moving in this direction in a magnetic field. So the magnetic flux is changing, and that's why a current is induced. Alright, so in a Fleming's left hand rule, first is the conductor, magnetic field, then the thumb is coming. But in a right hand thumb rule, what is Fleming's right hand rule? What is there? First is the thumb, then the magnetic field, then the current is coming. Alright, so be very, very careful. And Fleming's left hand rule, as we apply it in determining the direction of motion of a current carrying conductor in DC motor, so it is also known as motor rule. Fleming's left hand rule is also known as motor rule. And Fleming's right hand rule is used to determine the direction of the current produced in a generator. That's why Fleming's right hand rule is also known as generator rule. Okay, you must remember this fact. What I said, Fleming's left hand rule is known as motor rule, and Fleming's right hand rule is known as generator rule. And in Fleming's right hand rule, the thumb gives the direction of motion of the conductor, and then index finger gives you the direction of the magnetic field, whereas the middle finger gives you the direction of the induced current. Now another concept associated with Lenz's law. Lenz's law, actually it is based on conservation of energy. Why the direction of the induced EMF opposes the cause? Alright, so that you have to understand. Now you see here, when the North Pole is approaching towards the coil, alright, then if it is not opposed, then what will happen? You see here, when the North Pole is coming towards the coil, then some external agency is bringing the North Pole towards the coil. Alright, so who is doing the, what is happening here? That North Pole is coming towards the coil, and if it does not oppose, then what will happen? The external agency do not have to do any work. North Pole will come towards the coil by itself. Alright, and not only that, when current will produce in the coil, then what is happening? Energy is also produced. Means what? Work is done on the system and energy is also produced within the system. Then what will happen? It will oppose the conservation of energy, because we know that I always give you this example, that when your mom cooks food for you, then what your mom is doing? Mom is doing the work. Alright, mom is doing the work and she is feeding you. You are getting the energy. Is that clear? So, in this case, you see what is happening. The North Pole is coming by itself, means no work is done and energy is produced automatically. So, it is a violation of conservation of energy, isn't it? So that's why you see it should be opposed. The cause should be opposed. When the cause is opposed, then what will happen? That North Pole, now it cannot come towards the coil by itself. Somebody has to bring it, doing work against the opposition. And that work done will be converted into energy. So you see here what is happening. Lentz's law, actually it is nothing but another statement of the law of conservation of energy. Alright, so this concept you have to remember, because question comes like this: on which conservation law Lentz's law is based? Okay, so on which conservation law Lentz's law is based? Lentz's law is based on law of conservation of energy. Alright, so I am summarizing that electromagnetic induction. Regarding electromagnetic induction, what you must learn for your board exam point wise, that is what is magnetic flux, you must learn. You must also learn what is the definition of electromagnetic induction. Then you must learn the two laws, Faraday's laws of electromagnetic induction. You must learn Lentz's law statement and how to apply it in determining the direction of the induced EMF. Fleming's right hand rule also you must learn, and you should also remember that Fleming's right hand rule has another name. It is having another name. What is the name? Generator rule. Alright. And Fleming's left hand rule, it is known as the motor rule. Clear? Another point you have to remember, on which factor induced EMF depends. Induced EMF depends on the number of turns of the coil, and induced EMF depends on the rate of magnetic flux linked, rate of change in magnetic flux linked with each turn of the coil. I hope you can remember I wrote E is equal to N into delta phi by delta T. So it depends on N, number of turns of the coil, and it depends on delta phi by delta T. Means rate of change in magnetic flux linked with each turn of the coil. So this is the last lecture of the electromagnetism chapter. Whatever I said important for your board exam, kindly learn, remember and practice it. Thank you, girls. Now I just missed one topic, that is alternating current and direct current. All of you know that what is direct current, whose magnitude and direction it remain constant with time. Alright, and alternating current is what? Whose magnitude as well as direction it changes at regular interval with time. Just by a diagram I can show you. If you consider a direct current, if I draw the diagram, then direct current it is like this. You see the magnitude is constant and direction is also constant. It is direct current. But if you consider an alternating current, the alternating current it looks like this. Means you see what is happening. First of all what is happening, the magnitude is changing. Magnitude is becoming maximum and then it is decreasing, coming to 0. Then after that you see what is happening, it is changing the direction. This half cycle is in the downward direction. What does it indicate? The current has changed its direction. And not only that, at every instant of time the magnitude is changing. Alright, now in household circuit, we always use alternating current. We do not use direct current. Alright, now why we use alternating current? Because, what are the differences between alternating current and direct current? First point of difference is that in direct current, magnitude remain constant with time. In alternating current, magnitude changes with time. Okay, every moment the magnitude of the alternating current changes. Then second point, in direct current, the direction of the current remain constant, remain the same. But in alternating current, the direction of current changes at regular interval of time. Alright, so these are the important point regarding the alternating current and direct current. You must remember it. Now, the question arises that why in household circuit we prefer to use the alternating current? Because alternating current has certain advantages over the direct current. What are the advantages? Just try to understand. You cannot create the current at your home. Can you create? No. Here one more point I forgot to discuss, that is the difference between the alternating and direct current. You can write one more point, that direct current we get from electric battery. Okay, the battery is there, electric cell is there, we get direct current from battery and cell. They are the sources of direct current. And sources of alternating currents are alternating current generator, AC generator, as well as the electric mains that we are having at our houses. Okay. Now you see, you cannot produce the alternating current at home always. So electric power electric power stations, they are far away from our locality. Always you will see all the electric power generating stations, they are far away from our locality. So we need to transmit the electric power generated over a long distance. Alright. Now, alternating current, when it is transmitted over a long distance, then there will be less amount of loss in energy along the connecting cables. Alright, this is the first advantage of alternating current. Second advantage, it is very cheap and it is very easily we can generate alternating current. Alright, and then third point, that magnitude of alternating current you can change according to your requirement by using transformers. If you want to increase the magnitude of alternating current, use a step-up transformer. If you want to decrease the magnitude of the alternating current, easily you can do it by a step-down transformer. Alright, and it is very easy also to convert alternating current into direct current. Alright, by using the diodes. So these are the 4 advantages of alternating current over direct current, and very important topic for your board exam. So you must note down all these 4 points and learn and remember. What is the first point? Here I have written all the points according to its importance. So what is the first importance of the advantage of alternating current over direct current? AC can be transmitted over a long distance without much loss in energy in the line waves. Okay. Then second one, AC is cheaper and easy to generate. And third one, magnitude of AC can be changed easily by using transformers. And fourth one, it is easy to change alternating current into direct current. Alright, that's all about the electromagnetism chapter. Thank you, girls.